So in section 1.3, we introduce vector spaces. So we've seen special cases, very important cases of Rn and Cn. So these are the n-dimensional column vectors with real coordinates, and these are the n-dimensional column vectors with complex coordinates. And these are examples of vector spaces. And we need to know in linear algebra the precise definition of a vector space. So we can have vector spaces over the field of real numbers R, or the field of complex numbers C. So I'm going to use let's say the letter F to denote both R and C. So pick one, and but everything applies equally to the real numbers and the complex numbers. So what is a vector space? So a vector space is a set of elements the elements are called vectors. This is a vector space over the field F, whether F is the real numbers or the complex numbers, where we have two operations with two operations. So one is vector addition. Given two vectors, there's something we can call the sum of the two vectors. And scalar multiplication. And remember, in linear algebra, scalar is the name we use for number. It's the number. If you're working over the real numbers, a scalar is a real number. If we're working over the complex numbers, a scalar is a complex number. And vector addition has to satisfy following properties. So what are the properties that vector addition has to satisfy? For all vectors, let's say u, v, and w in the vector space, addition is associative. We have associativity. That means u plus v plus w is always the same as u plus and v plus w. Remember, vector addition is a binary operation. You can add two vectors. So here we're adding u and v. That's a sum of two vectors, but then this is a new vector. And this vector plus w is again a sum of two vectors. And similarly, on the right side, we have sum of two vectors and then another sum of two vectors. Associativity says this is always the case. Commutativity. I apologize if my writing is illegible, but everything is done very neatly in notes. So just have to keep looking at the notes all the time. U plus v is v plus u. There's a zero vector. So there exists a vector 0 in V, such that if you add any vector to 0, it doesn't change the vector. And every vector has an additive inverse. So for all vectors V in vector space, there exists a vector W in the vector space, such that V plus W and W plus V both equal the zero vector. So these are the four properties that vector addition in a vector space has to satisfy. There are also properties that scalar multiplication has to satisfy. In scalar multiplication, you take a vector v and a scalar c, and you can multiply the vector by the scalar. So let's see how that goes. So for all vectors u, v, and w and v, and scalars, so A and B is the notation I used in my notes. Scalars A and B in the field piece of note. So we have the following scalar multiplication properties. It has to be the case that, first of all, if you multiply a vector by the scalar 1 times v is v. So all vectors v. That's for a second. So scalar multiplication. 1 times v equals v for all vectors v. If you take AB and multiply by v, that's the same as A multiplying into v times v. A plus b times v is AV plus BV. And A times v plus W is AV plus AW. So these are distributive laws for scalar multiplication and vector addition. This is a kind of associativity, and this is just a basic property you hope you want to be satisfied. So any set in which we can define operations that satisfy these properties is a vector space. And there are lots of examples of vector spaces. So first of all, Rn and Cn are the fundamental examples. These are the spaces of n-dimensional column vectors, and we define coordinate-wise addition and scalar multiplication. But there are other vector spaces. For example, those I'll call P sub n of R. So these are all, I'll just call it P of R. These are all polynomials with coefficients in R. So you might have a polynomial f of x equals 3x squared plus 2x minus 9, and g of x is 7x cubed plus x minus 17. These are polynomials, and you know how to add them. This is 7x cubed plus 3x squared plus 3x minus 26. And if you multiply a polynomial by a scalar, let's say 5 times f of x, so that's 5 times this polynomial, 3x squared plus 2x minus 9. You multiply coordinates, this is 15x squared plus 10x minus 45. So polynomials with coefficients in R form a vector space with the usual rules for adding and multiplying polynomials. Here's an example from calculus. I'll call it C01. This is all continuous functions. F from 0, 1 into the reals. So take a function, y equals f of x. We define the sum of two functions, f plus g of x, to be f of x plus g of x. And a scalar times the function f of x is just c times f of x. So in calculus, you spend the whole year studying continuous functions and their derivatives and integrals. And the set of all continuous functions, let's say just defined on 0, 1, to make it very specific, is another example of a vector space. And linear algebra is nothing more than, or is precisely, the study of vector spaces. Now, a subset W of a vector space V is a subset of V with the following properties. First of all, the 0 vector belongs to the subspace. W is closed under vector addition. That means that if x and y are vectors in W, then the sum x plus y, we know it's in V, but this is also in W. And W is closed under scalar multiplication. This means that if B is any vector in W and C is any scalar, then C times W, C times V is also in W. That is what a subspace is. And there's a simple lemma which says the following. If so, a subset W is a subspace if and only if W is not empty. So this is the symbol for the empty set. You can see in the appendix. If W is not empty and W is closed under linear combinations. That means if W1 up to WK are vectors in W, and C1 up to CK are scalars, elements of the real or complex numbers, then I can multiply W1 by C1, I can multiply W2 by C2, and so forth. I can multiply WK by CK. I can add them all up. That's what we call a linear combination of the vectors. So W is a subspace if and only if it's a non-empty set of vectors closed under taking linear combinations. And it's easy to see if you just operate two at a time that every linear combination of vectors is contained in W. So that's just very important. It's elementary, but it's a very important observation. And there is a converse, which says, actually, I filled it into this. If you have a non-empty set which is closed under taking linear combinations, then it's a subspace. The set of all linear combinations of a non-empty finite set of vectors is a subspace. And every subspace is closed under taking linear combinations. So this is the fundamental definition of a vector space. And you really need to know this by heart. You should actually memorize the definition of a vector space. This is something that it is essential to know. And the more time you spend studying this and the more time you spend on the exercises, the better you will learn linear algebra. And this is all there is in section 23. So,